Good afternoon, everybody, and welcome to episode 11 of Trench Talk, a series of webinars targeting the geothermal industry and hopefully share some ideas and exchange thoughts and comments. These webinars are only valuable as a live webinar if you participate. So please use the chat window, make comments, ask questions. If we don't get to all of them, we will reply with answers or give you some feedback. So I appreciate you all taking the time to join us today. The title of today's webinar is Copper Top. And for those Matrix fans out there, you know what I mean. I also want to thank our sponsor this month is Source Rock Geothermal. They're a company that will provide turnkey horizontal or vertical loop systems pretty much anywhere in New York State. So if you're an HVAC contractor and you currently don't offer geothermal, this is a very valuable resource to get you started quickly and take advantage of the market demand. I want to review some fundamentals here so that we're all on the same page. The first law, actually the first law of thermodynamics. Energy can neither be created nor destroyed, only altered in form. Fundamental thermodynamics principle. Units of energy. Just to review, a BTU, a British thermal unit, we seem to be exclusively using BTUs in the United States to characterize energy. The rest of the world treats thermal energy and electrical energy with the same units, a kilowatt hour. There's a direct conversion from a kilowatt hour to BTUs. So in essence, to steal a line from Romeo and Juliet, what's in a name? That which we call a rose by any other word would smell as sweet. And we can alter that slightly. That which we call a BTU by any other word would still be energy. Storing energy. How do we store energy? Well, the copper top. A battery, very familiar to all of us. Another way to store energy is pump storage. We can put electricity in to drive water up to a higher reservoir, and then when we want to capture the electricity output, we'll let that reservoir lead through a turbine to a lower reservoir. Pretty straightforward. And then, of course, one of my favorite companies, Tesla Megapacks. If you follow Tesla at all, this is going to be a very fast-growing segment of their business. Each of these has a value reflecting the cost and overall benefit. So there's another form of storage, and that's what our guest is going to talk about today. I'm thrilled to have my good friend Jens Ponikau join us. But before we turn it over to him, I'd like to share with you just this thought. The most interesting man, you know, the guy promoting Dos Equis. That guy. However, I would say that our guest is as much interesting as the Dos Equis guy. Jens is the president and founder, co-founder of NY-GEO. I call him the chief creative officer of Buffalo Geothermal. He also happens to be a doctor and flies his own plane. But let me warn you, if you ever take a trip to Germany with Jens, you'll be drinking a lot of good German beer. I speak from experience. So without further ado, I'm going to turn it over to Jens. And I will stop sharing, and Jens, you can fire up yours.
Good afternoon, everybody. Yeah, I don't think I'll forget that moment or that trip to Germany with John, specifically when I got in the car with him and I said, "Oh, did I tell you that you need to be really, speed ready when we go the Autobahn?" He said, "No," but that's when we entered the Autobahn. So it was actually pretty funny. He was quite awake even after a long trip on the plane here. Anyway, let's talk about geothermal. Let's talk about storage. And as John mentioned, we are essentially a geothermal company here in Western New York. We have certified geothermal designers on staff. I myself, I'm one of them. We specialize in large-scale multifamily and commercial projects, especially retrofits. And we're pretty much vertical integrated. That means we do everything from design, installation, manufacturing. And we focus totally on quality and efficiency. Nothing else for us matters. And we do that for fixed price. So there are usually no change orders unless you start to change the scope on us. And I just want to start off with just setting the stage here. These are some graphs from the EIA, and this is the total amount of energy use, the consumption, essentially by end use in a building. So if you look at New York State, it's a little bit different than the rest of the US because it has a relatively high heating load. 56% is heating. Only 1% of the total energy is cooling. But that 1% is completely driving the summer peak and the capacity which needs to be installed in the grid. We have approximately 7-8 gigawatt of difference between summer and winter peak currently, but that extremely small amount of total energy is driving this relatively high difference in peak demand. Now, what do you think is going to happen when we electrify all the buildings and we're adding another 56% of weather-related peak to the grid, to that 1% we have right now? And that's when it starts to sink into you and saying, what is going to be the peak use in our building after electrification? I really like that slide, not because I took it myself, but because it exemplifies, what part of the current system, the problem with part of the current system is. This is a look out of my hotel room in April. And you can see here, there's a cooling tower coming on, and you see the fumes coming out here from the vapor. And you can nicely see that it's operating in April because obviously there's a lot of thermal energy in a hotel due to its energy density. But about 100 feet away, you see another smokestack here. That is the boiler turning on to make hot water. So in one way, we are rejecting energy, thermal energy, into the atmosphere. And at the same moment, in the same system, we're burning fossil fuels to make thermal energy. So it's kind of silly nowadays to think about it, because why don't we store this energy here? We're currently rejecting in the atmosphere and use it for other thermal needs. And it would avoid those kind of thermal energy it takes to make hot water or maybe even heating at the same time in another portion of the building. So part of the issue is that our system currently is utterly inefficient, and we don't preserve energy. We're actually trying to getting rid of it. We're wasting it. The same thing can be said about, this is how air source heat pumps would operate if they are put on a building. They would reject the heat out of a zone, and in the same time, another air source heat pump would try to take it out of the atmosphere. And the BTUs or the kWs are getting lost. The other problem is that obviously air source heat pumps are much more sensitive to declining temperatures. There simply is lesser heat in the air. And that affects both their capacity and their efficiency. Ground source heat pumps are coupled to the ground. They have no idea how cold it is outside. They only see the ground temperature, including the energy which has been stored in the ground before. So how big is that whole problem? Well, if you're looking at how much are we currently using in terms of energy and how big our building loads are, and this is the data for New York only, you can see the entire thermal need of all the buildings together for space heating. And this is the residential and the commercial load. This does not include the hot water, and it does not include process heat. And that is 557 tera-BTUs. That's an incredible high number. How much is that in peak? So this is actually the building use is not the fossil fuel amount of heat going in there. This is actually the building load itself. You can actually convert that by looking at the full load hours here, and they are published by NY-GEO. And again, the 557 tera-BTUs, that is also a published number by NY-GEO, which they have estimated. And you can calculate now the peak usage by matching it with the weather data and looking at the full load hours. So the weighted average full load hours is about 1,300 in New York State, and that equals to 123 gigawatts. Keep in mind, we only have currently a winter peak around 23, 24 gigawatts. So we would probably add at least 100 to that. That's a normal amount of energy. So again, keep in mind, that's without the hot water, this is without the process heat, and this is without all the other electrification measures we're going to put on the grid in the next few years, including EV charging. Slowly, state agencies after the CLCPA, the Climate Leadership and Community Protection Act has been implemented, are starting to wake up and say, oh, you know what? The lower lines here, was our forecast for the past, but now if we're thinking about implementing this, I think with a lot of heat pump use and retrofitting buildings and make them more efficient, we're ending up at about 70 gigawatts. I'm not so sure if that's enough. But, at least they're starting to wake up and saying, this is getting real. We're putting an enormous amount of new load onto the grid. In comparison, this 120, 130 gigawatts is dwarfing what they're predicting for the peak coming from electric vehicles. Everybody is worried about charging electric vehicles. That's only 3 gigawatts. They upped this now to about 6 gigawatts by 2040, but it is dwarfed by the amount of heating peak which is occurring on the coldest day of the year. Nothing is anything compared to heating energy needed. So I remember some of the staff members or some other legislators were responding and said, well, we understand we need more energy at peak. That's why we are actually putting together, legislature to mandate and require energy storage. So right now, this was 3,000 megawatts, so about 3 gigawatts, and now they upped that to 6 gigawatts by 2030. And I responded, well, let me put it in perspective. The heating peak alone of 100 plus gigawatts, your 6 gigawatt energy storage will last you about 4 minutes in the night. And this is when it really sits in and starts to hit you and saying, we got to figure out a different way to store energy. And we cannot just look at electric energy. We got to think about thermal energy. And we have to make sure we don't waste the energy and reject it into the atmosphere when we need it at another time point. So we need thermal energy storage. This is the profile from the heat pump study done by Hugh Henderson for NY-GEO. And you can see here nicely, this is the peak profile of 17 buildings across the state. These are residential systems. And it shows you that the black curve here is at about -5 degrees temperature, peak temperature. And the red curve is at 0 degrees, and then it's 5 degrees. So the warmer it gets, the lesser amount of kW the heating systems are using. But it also shows you, so this is totally outside temperature dependent, which we would expect. Heat loss is linear. However, it also shows you that the peak of the heating is occurring around 7 o'clock at night, and not what we're looking at in terms of our electrical grid peak currently, which is all cooling dominated, which occurs in the early evening hours. Right here, the heating peak does not occur. It occurs in the morning. So the difference is that we don't have the solar recharging our electric batteries, and we only have to bridge 3 or 4 hours here. We have to bridge the entire night with a much higher load. And then we get the super peak at 7 in the morning. That is really our challenge. So in comes into the equation a couple case studies I want to run by you, because we started to learn to how we can actually look at energy, how much the geosystem is impacting it. And this is a building which I predict will become famous, because not only did the owner and developer go the extra mile to build a very, very efficient system, but we also had NY-GEO putting all their instruments and measurements on there. So Hugh Henderson actually is measuring this as a third-party MMV project for NY-GEO. So my thanks to NY-GEO that they actually took this on and provide the third-party monitoring here for Zero Place. Zero Place is 46 New Paltz in the Hudson Valley. It gets there very cold and very hot in the summer, very cold in the winter. And it is extremely efficiently built, 46 apartments, 6 commercial spaces. I would argue this is a typical mid-size mixed-use building here in New York. Now, if you look from up, it looks from above, it looks a little different, almost like a spaceship. You can see it's plastered with solar panels, including the elevator shaft and including the awnings on the southern side. So it has a 180 kW solar system on there. And the idea was to build an extremely efficient building and pair it with solar and geothermal, and then understand the way the energy flows in there. We put in a geosystem for this. You can see here, these are 15 400-foot wells. They occupy only about 50% of the building footprint. That was enough for the whole building. I mean, if we would maximize the entire footprint here, we would probably have enough room for a 30-story building. I would argue even nowadays a little bit more from what we learned here from that building. The loop field is about 67 feet per installed ton. So you can see we pushing the conventional wisdom, what we think, how many feet per ton we need. And just to introduce the project here. They're equipped with water furnace heat pumps, 1 per space, per zone space. That means 1 per apartment and 1 for the commercial areas, and also a couple of them for the common areas. But we also make all the domestic hot water there in this building with water-to-water heat pumps. For the water usage, we use a stage design. That means we preheat it to expose the first heat pump to colder temperatures, which significantly increases their efficiency. And then a second set of tanks is doing the final conditioning to bring it up to 125, 130 degrees. We store about 640 gallons for that building here. And, one of the heat pumps, they're designed that if one of them fails, the other one could still carry the entire load. The trick here is that all the multifamily buildings we have looked at in New York State are actually cooling dominated due to the high energy density. That means they reject more energy into the loop field than we're actually taking out for the heating season. That also means that by including the hot water, which is cooling the loop in the summertime or keeps it cool, we can make the loop smaller. And that allows us to offer the hot water equipment for free because we have large savings in the loop field design and implementation of it. So it's a little counterintuitive. We give you hot water for free if you put it in there, but the system can be made smaller and much more efficient if we're having this cooling effect by taking the thermal energy out of the loop in the middle of the summer or help cooling the loop for domestic hot water production. Again, this is just an idea about the stage design here. The COPs are going up due to the stage design, and we take advantage of exposing the heat pumps to as cold temperatures as we can to increase their efficiency. Then the other design feature here is that we have an adaptive pumping solution. You can see here a flow center purging all the air out continuously and providing the flow to the two heat pumps here, to the two circulation pumps here. They're pressure regulated. They sense the back pressure on how many heat pumps are actually online, and they adapt accordingly. So the average annual pumping power is only 396 watts that way. And that is, what I feel a very unusually low number. The trick is here that we keep the pressure drop low. We have no balancing valves. The loop fields the boreholes are slightly shallower. They're only 400 feet. So we spread out the floor through more circuits. There are no restrictions in there. For example, no balance valves. And that helps us to keep the pumping power as low as possible. The trick is really to only pump as much as you need and to have smart pumps here to increase the efficiency. The entire building does not have any gas lines. It's completely emission free. The only gas line going in is in the emergency generator as a backup. So the interesting part here, and this is now looking at the energy flow or the total energy use. So this is the electrical use for the GEO system. And this is the summertime over here. And this is the winter time. And you can see that the system uses just about as much energy per month in the wintertime than it does in the summertime. Also, the hot water production is slightly less in the summertime compared to the wintertime. And that is probably due to the fact that the cold water coming in is much warmer in the summertime, around 60 degrees max, compared to the wintertime where it drops down to around 45 degrees. Then we have the shoulder season where, of course, the space conditioning is going down. It doesn't go down to zero because some people like it warmer, some people like it colder. But it's significantly less than in the wintertime. So looking at this from a little bit different perspective, and this is energy going into the loop, and this is at a 50-hour span around April this year. And I just want to emphasize here, this is really, instead of rejecting the thermal energy into the atmosphere with the cooling tower, we're actually putting it into the loop field and using it as a different time. So the red line here is the temperature coming back from the loop field. And you can see it's around 50 degrees. Well, we're slowly entering cooling season here. And you can also see that the temperature going in changes relatively wildly. Within a short amount of time, it changes by about 6, 7, 8, up to 10 degrees. That means that, and this is due to different heat pumps running in either heating or cooling, or whether hot water is generated or not. But you can also see that the amount of energy going in and out of the loop field is changing dramatically, and the loop field is reacting instantaneously. It's either taking energy in immediately or taking energy out or putting energy out. Similar to an electric grid battery, which is stabilizing the grid and essentially balancing it. And again, this is instantaneous. It reacts immediately to input and output. And this is something I probably didn't expect. I always looked at thermal energy to be slow, but no, the energy has nowhere else to go. As John said, energy cannot be destroyed. It has to change its form. So this is thermal energy going in and out of the loop field instantaneously over, in this case, a 50-hour period. Looking at this a little bit more granular, this is now 2 hours, and you can see how it jumps up and down. In this case, we are rejecting energy into the loop field because the entering water temperature is warmer than the temperature coming back from the loop field. And the loop field temperature coming back, it's pretty much equal. That means there's a huge thermal mass back there. And no matter if I take energy out or in, the battery is so large, it hardly is reacting to those instantaneous in and outputs. So this is over a 2-hour period, and these are 1-minute sample sizes here. And within 1 minute, it starts to react immediately by increasing or decreasing its temperature. But it's not reacting very much because the thermal mass is so enormously high. Now look in this now at a very, very large loop field. And this is actually coming from the Riverhead demonstration project here. This is a slide from the final report. And you can see this is a district pilot project from National Grid on Long Island, where they looped about 10 single-family homes together. And this is reacting in the same way. So this is the winter time, beginning of January. Then they're storing heat in there, heating up the ground to about 80 degrees. Or correction, this is actually the ground temperature coming back. So it's about 75 peaking. And then the temperature goes down again, where the loop field temperature is, or the loop field is extracting heat from the ground. And 1 year later, it's doing the same thing. It peaks again around 75 degrees. And in the winter, it draws the temperature down again. And you have all those little events here in between where the loop field is reacting to input and output. You do have sometimes cold spans. You have warm weather. And this is all reflected in here. So I always say, geez, if we would have a battery on the electrical side, which would provide 75% of the entire energy for a home. And keep in mind, for single-family homes, that battery is 6 inches in footprint. We only use single boreholes anymore on average single-family homes up to 3,000 or 4,000 square feet. And it's going to last for 6 months through the whole winter, and would be automatically recharged by solar energy in the summertime, which we're putting in there. If we would have that on the electrical side, we wouldn't have a grid anymore. We would have solved all our grid problems. So I call it geothermal on a small footprint, at least for single-family homes, but this is actually what this thermal battery in the ground is doing. Now, let's go back to this space and heat extraction and contraction here, which we're seeing. This is again a multifamily building. This is again zero place. And we have different measurements here, different risers. So the blue line is the north side, where we don't have much solar gain. And we probably are using more heating. So this is in February. And this is again looking back 48 hours or 50 hours here. And the blue line is the amount of heat extracted, the delta T of the loop field, coming from the northern portion of the building. You can see it sometimes dips down to like -8 delta T. So we are actually extracting a huge amount for the northern portion of the building from the loop field. The red line here is the hot water production. When those big heat pumps turn on, and when they both turn on at the same time, we're looking at a -10-degree delta T. So we're pulling out an enormous amount of energy just for hot water production. The central portion of the building is the green line. Well, it doesn't have as much heat loss because it does have much lesser outside wall. This is why it sometimes even has a positive 6-degree delta T, meaning it is actually operating in cooling mode sometimes, probably during the day in the middle of February. However, the northern side doesn't have that gain and is running in cooling side. So here they're exchanging only energy in between different portions of the building. But look how the loop field is reacting to in and output in that way. Now, the magenta line here is the southern portion, and this is the warmest one. So this is where we have the most amount of heat rejection coming in February into the loop field. Everything which is above zero is actually rejecting heat. Everything which is below zero is extracting heat out of the loop field. But you can see how there's a lot of energy sent around the building, it all goes through the loop field, but this water is mixed before it goes in and out. So there's a lot of exchange just between the heat pumps themselves. Not a single BTU or kW is wasted. It all finds its way back to other sides of the building which are operating in heating mode. Now, this is again Riverhead. I'm jumping a little bit because I want to demonstrate a few things in multiple projects here. This is again looking at 10 single-family homes on Long Island, which have a common loop field. So this was monitored in 2018 and 2019, also by U. Henderson for NY-SERDA, and actually for National Grid in this case. And you can see here, this is the amount of heat coming out of the loop field. January, February, March, a lesser amount every month. But this is really pulling heat out of the loop field, almost putting none of the heat in. That switches around May when this neighborhood starts to go into cooling mode. But look how much bigger the energy is being rejected into the loop field. And then it starts the next year. Well, this is actually coming out of 2018 and this is 2019 then. But the entire point is that the maximum of energy being reacted is much, much larger in the summertime than what we extract out of the loop field in wintertime. As another example, just to visualize that a little bit differently. This is, the red is the summertime. This is the heating. And the blue is this is the wintertime. And the blue is the summertime. This is the cooling energy. And you can see the peak cooling is about twice as high as the peak heating in terms of loop field energy. We're extracting on the peak day about only half the energy from the loop field than we're putting into the cooling. In other words, the cooling is so high, much, much higher than what we're pulling out of the loop field in the wintertime on a single day. Now, why is that? And it's important to understand that you know, the space is a very different heat than the actual loop field. So for example, on an annual basis, the annual space load, the space was trying to use for heating purposes used actually 310,000 MBTUs. The cooling was much less. So there was only about a 72-28% ratio. However, the loop field almost saw the same amount. And why is that? Because in the wintertime, we get a certain amount of heat energy from the compressor power, which ends up as heat in the space. In the summertime, that compressor energy needs to be also rejected. So that compressor energy needs to be added to what the loop field is seeing here. Here's another way to explain that. So this is heating operation. This entire neighborhood was using 310,000 MBTUs, but only 86 of those 310,000 186 come from the loop field. This was the compressor power, this was the pumping power, and this was the fan power. So the total energy use of the system was approximately 310,000. And if you then look, the COP of the system on average was about 2.8. Not really the greatest, but I think they learned a lot on how to make this more efficient. And a lot of this was due to much higher pumping power in that system design. Now looking at cooling, the opposite is the case. Cooling load was only 118,000 MBTUs, 118,000 MBTUs, and but there were 167,000 rejected in the loop field, because we also have to reject now the compressor power, the power of the pumps, and the power of the fans. That all otherwise would end up as heat in the building. In this case, it needs to be also rejected into the loop field. That's why the loop field sees much more energy being rejected into it in the summertime than it gets extracted from in the wintertime. That also means that every building pretty much makes all the energy it needs by itself. All we need to do is store it for 6 months to heat it with in the wintertime. So this is actually a great thermal battery. We're putting heat in. This is not new. What is new is that we have really, really good means now to quantitate this and understand the flow there. The loop field actually stores all the energy of the building in the boreholes for the whole year, and it's enough to provide all the heating needs and all the thermal energy for the whole heating season. It does not necessarily to be connected to other buildings. It does it by itself. It stores it underground, and it makes all the thermal energy it needs. The key is the storage component here. If you go low enough in temperatures with a loop field, below 30 degrees, it usually does not dip below that, since it's making ice around the boreholes. I show you that in a second, which releases a large amount of heat due to the phase change. So it's part of a phase change technology, and it actually reacts immediately to in and output. Nothing gets wasted. So this is, again, zero place. And I just want to emphasize a few things again. And this is looking back at 50 hours. And again, the red line is the temperature of the water coming back. The blue line is the temperature going out. And you can see nicely, it gets colder in February. This is February 18th around, and looking back 50 hours. And it gets colder, and now we're entering a cold span here for about a day or two. And the loop field automatically increases its delta T. So it actually can respond to a much, much larger amount of peak demand by just increasing the delta T. And that way, it can deliver an enormous amount of peak energy. This is another way of looking at it, and it just determines how much this was here. It quantitates it. So this is 0 delta T at the loop field, If we're going down here, we actually are operating in cooling mode. And you can nicely see here, this is really between January 11th and February 12th. And you can see how the delta T goes up when there's a more heating need. And we had -6 degrees in New Paltz, where zero place is. And we were pulling out up to about close to 380 MBTUs per hour. Another way of looking at this, and this is one of my favorite slides here from you Henderson's report to NY-GEO. It shows you about a 6-week period between January and middle of February. And you can see the loop field was constantly taking out heat and delivering heat, anywhere between 100 and 200 MBTUs, about 30 to 60 kW. And it was delivering this over the entire peak heating season. You can see outside temperatures here. These are the average daily temperatures. This is not the peak. You can see, again, if it peaks down here, so we had a really bad cold span here in the beginning of February. And this is when the loop field starts to automatically deliver more MBTUs. That's where the peak goes up by increasing its delta T. It's ingenious. It's a reliable source which immediately reacts to in and output and starts to increase its capacity when you need it. Overall, now this is again zero place. This is the entire year. It peaked at about 75 degrees due to the cooling of the hot water generation. And it went down to about roughly 42 degrees incoming temperature. Some could accuse me of making it too big. We designed it for about 34 degrees. It ended up to be designed to be about 42 degrees. So there was a lot of in and out of energy, which we didn't account for, or which we were unable to model for, which is actually we're measuring and seeing. But the point is, we start to put energy in, we heat up the ground to about 75 degrees, then we're entering heating season and we're getting this energy back. And then the loop field simply does not budge anymore, no matter how cold it gets outside. Again, we measured -6 degrees outside temperature. This is where this is going down a little bit in the beginning of February. But other than that, it was a reliable source of energy and it was always delivering. These are now 10 single-family homes in Buffalo, New York, randomly selected. And you see a similar trend. So this is what I call geothermal on the small footprint. This is a single 6-inch diameter borehole feeding single-family homes. And we are measuring this under an NMV contract for NY-GEO. And you can see again, similar trend. It heats up to about 70, 75 degrees. And then the heating season comes. Now we're getting into October. This is essentially the end of the year. And we're pretty much close to where we were when we started this. So here you see the phase change. It doesn't drop much below 30. And then we're starting to put the energy in. And here's when we start taking the energy back out. So the same concept works on single-family homes, which don't have that much of internal gain in even very heat-dominated climates like Buffalo, New York. And in those here, we actually also make all the domestic hot water production. So these are all buildings which are 100% on geo. A lot of them don't even have any gas lines or any fossil fuel sources, not even for the generators. How important is this? Well, it's utterly important, I would argue. You can see here, to have that thermal battery avoiding any kind of battery peak in the electrical system or any kind of peak is crucial, because that thermal that thermal peak is putting our grid on the edge even today. This was January 16th, 2022. And you can see this was actually the night where the Buffalo Bills beat the heck out of the New England Patriots. It was also the second coldest NFL game ever recorded. And then I believe we were at also like -6 or -7 there. How do I know I was there in the stadium? And believe me, it was cold. The good part is there was not much wind blowing. The bad part for the grid was there was not much wind blowing. This is why suddenly we saw peak prices going up to $2,000 per megawatt hour. Normally we see about $2.5 per megawatt hour. So you can see how sensitive our grid is to temperature-related events, in this case, heating. And keep in mind, we only have 10% of the buildings on electric heat. Imagine if we switch this over to 100% and we don't have that storage component. Now, this is the 10 single family homes here in the Buffalo area. And we looked it up. This was at the coincidental peak in 2020. And they were operating at an average COP of 3.74. And we were pulling an average of 9.22 kW out of the loop field as thermal energy during that peak hour. Now, I raised the question, how much is that worth? Because if we don't get that energy out of the thermal battery, we would have to have an electric battery supplying the electricity to have either an air source heat pump running at a COP close to 1 on an absolute cold night like this, or we would have to use electric battery backup or electric heat to begin with. So this actually would avoid 9.22 kW. And how much is that worth? How much do we pay for 9.22 kW? Well, it's pretty easy to answer that question today, because you can see here, we know how much a kilowatt hour is in the battery grid storage market. Currently, we average at about 567 watts as dollars per kilowatt hour, I'm sorry. And that is worth for an hour about $5,200. Well, for the entire day, if I want to bridge 24 hours with a battery, that is worth about $98,000. And these are actually numbers. This is what New York State paid for last year for a grid battery storage capacity, $567 per kilowatt hour. So the peak day actually is worth, if we want to bridge an entire day, it's worth about 100 grand. That is what the borehole was delivering in equivocal energy, thermal energy, during the peak day on average in a single family home. And now you can argue, what about if the wind doesn't blow for a couple of days and it doesn't really, the sun doesn't shine, obviously, because it's cloudy days, and we need to bridge more than a day. Maybe we need to bridge a month. Well, for a month, that storage capacity was worth about 1.8 million. Is this a realistic number? Not really, but what we need to get used to is that we need to not only store this energy, but we need to also look at on how we supply it or replenish the alternative, an electric battery. Now let's look at zero place again, what the numbers are there and what they would be there for. Here's zero place again. And that building was using for the winter peak about 31 kW. And that is for space conditioning and hot water at -6 degrees. Interestingly, pumping power during peak time was only 1.47%, and the total energy usage with all the appliances and everything else was about 51 kW. There was obviously no solar there, very different in the summertime. 24 kW for the space conditioning, including the hot water. Another 25 kW roughly for about the same amount of peak energy usage we had in the winter than we had in the summer. But here now the solar kicks in. At that peak moment, it produced 161 kW. So it actually exported power to the grid. We don't have that luxury in the wintertime. This is why the thermal battery storage becomes so utterly important, because here we used 50 kW in grid power. Here, the solar system was producing a way excess. So it's not really the cooling problem in the future. It is really the heating problem because we don't have the solar gain. Last few slides here. Now look at that number. Zero Place pulled out a peak of 106 kW during peak heating, and that's coming directly from the loop field. For the peak hour, this was worth about $51,000. On the peak day, this avoided $670,000, almost $1 million for one day. The entire system was costing $1 million to put in. And now you look at 1 month, and it avoided about $18 million of energy storage. Now you can say, well, we don't really need a 4 months of energy storage to power something like that. But there might be a couple other arguments against that. Keep in mind, when we look at heating systems, we now want to have a heating system which doesn't bow down in efficiency and which doesn't bow down in capacity, independent from the outside temperature. We must cover the full load without supplement resistant heat. We must not only reduce the heating, but also significantly the cooling, and it must make all the domestic hot water without electric resistance heat. That's our goal. So it must do that not only for one peak hour, it must do that for the peak day and for the peak month. So now look at this, what it avoids beyond the actual storage capacity. Keep in mind, how much is it worth if we don't need to recharge that battery? If we don't need to have the power plants anymore and the windmills anymore? If we avoid that entire capacity because the battery lasts for 6 months and is automatically recharged? What about the transmission lines to be avoided? Not just the pure battery cost. Just as a reminder, we're building right now a transmission line up to Montreal, to Quebec, and it costs $6 billion for 1.2 gigawatts of power supply, and it's for the summer only, because our Canadian friends need it for heating in the wintertime themselves. They don't have a cooling problem up there. These are enormous costs a local battery would avoid. Keep in mind that solar capacity is very limited in the winter month. We don't have it. And the peak occurs in the early morning hours where we simply don't have any sunshine. We need storage. Keep also in mind that in the grid of the future, done mainly by wind. The wind is intermittent. We had 74 instances in 2020 when the entire wind fleet output remained below 100 megawatts. That's below 5% of capacity for more than 8 consecutive hours. That's pretty much every 5th day we were off for more than 8 hours. How are we going to bridge that gap with storage if we don't have thermal storage when we need it? And again, the nice thing is it recharges automatically in the summertime. We don't have to worry about all those things. Another aspect is that the capacity does not degrade. We know the ground loop is going to last for 200 years. They're not going to bow down, and they don't have to replace every 10 or 15 years like an electric battery would have to be. So the net present value is so much higher of that thermal battery in the ground. So the key points, if you think about this at storage, we know that other countries who went through this electrification, their peak is now occurring and shifting to 8 a.m. in the morning where we don't have any solar gain. It is also likely that in New York State, we currently underestimate the peak demand from the electrifying, specifically the heating sector. And we are potentially overestimating what solar and wind can supply and for how long. Geothermal is the only renewable energy source which has a built-in storage capacity automatically built in, which is essential for us to meet those CLCPA goals. And in my opinion, it's really the only technology which has a chance to meet the enormous thermal peak requirements in New York State. And we can only do that if during peak time, we have 70% of the thermal energy coming from a reservoir, from a thermal battery on site. And that's what geothermal is delivering. Just want to say thank you for everybody, specifically you, Henderson here, who does a lot of the NY-GEO and utility monitoring, and also Pasquale Strocchia here, the energy consultant, and who is also monitoring Zero Place and helped to gather some of the data as well. Other than that, sorry, I'm a little bit over my time, but I just want to open it up. I have more time here. We don't have to cut it off that quickly, but I just want to open it up for Q&A here. John, are you there?
Yes, I am, Jens. I'm going to take over sharing the screen to finish this out. I can do this.
Okay, there are a couple of questions. Maybe we can get started from the comments in the chat. Don't studies for CLCPA show, based on an assumed mix of air source and outputs, that demand on grid will be winter heating dominated? Yes, it does. That's the point. Doesn't your talk show that heat energy flow is cooling dominated? Yes, it is. So the energy flow is, however, and you saw the peaks, which are, the trick is, we still need to, if we are the mix, how shall I answer that? The demand on the grid will be heating dominated. That is correct. We currently, not every building has air conditioning, so we will see a much larger load there once we switch over to heat pumps. And the trick is actually that the heating demand is so significantly higher. I don't really look at those studies because for me, they're missing the point here. They're underestimating the amount of heating energy needed. They're still looking, NY-GEO still is looking at a summer peak, not a heating peak. If you then analyze how big the energy use actually is, I think we're looking at a striking peak unless we are changing the way we build buildings and we actually are storing energy. I hope that answers a question from Peter here. He's got another one. The ground temperature swing works against you. Putting additional heat into a warmer ground is harder. Doubling the field size would reduce the ground temperature swing and make systems more energy efficient. Yes, that is correct. But if you are now using also balancing the loop field by putting hot water in and out, specifically putting hot water in, pulling heat for hot water out 24/7, 365, that is actually, in our experience, nicely balancing the loop field. What is the optimal trade-off between loop size and efficiency? I think we're looking at, we usually look at in the very low 30s as a design criteria in the heating time, and we are not trying to overshoot in any way above 75 degrees because we are using methanol as a transfer fluid. And as you know, that is limited, at least here in New York State, for having a certain safety margin between the flash point of methanol, which is 125 degrees, So the code right now requires that. I'm not sure how valid that all is, but we're designing for 75-degree cooling temperatures, peak cooling temperatures, which we've shown you. And we're trying to design not to exceed, not to go much lower than 30 degrees on the heating side. Carl Neubert, one more question. Would you consider hybrid solar cooling in summer to increase efficiency and warming in winter to keep the panels slow and ice-free? Yes, I mean, I think it's important that we have solar as an option in the wintertime, even if it's not performing as well. Snow on them is certainly not good, specifically when they're cover them on a long time. To have in any way snow melt system for solar would be extremely beneficial. Yes, but even the solar, I would argue, would need a significant amount of storage. But I think there's a point to be made. What we're learning here, we're learning at Zero Place that the solar does not change the peak very much because it happens at different hours and times. So again, there we would be looking at either shifting the thermal peak further if we can do this, if we can have bigger tank storage, etc. Storage is the key. But what I'm trying to emphasize that there's an enormous amount of value to have, no matter when the peak occurs, 70-75% of that thermal energy coming actually from the ground. Other than that, I don't think we can actually make that transition to renewable energy if we don't emphasize that. Any more questions?
I don't know if you picked up in the chat window, Margot asked, what would happen if you did a heat-only project and rejected no energy in the loop in the summer?
Then the loop does, I mean, it still acts as a storage, but the storage energy does not come from the building anymore. We're doing this right now for the New York City Housing Authority, where we're doing only the hot water. So we're putting heat out of the loop 365 days a year. And the loop field has to be significantly larger, and the boreholes have to be much further apart, about 30 feet apart, because we are not putting any heat in, we're not replenishing that heat. So the heat actually has to come from further away, much further away from the boreholes, and the boreholes have to be much further apart so they don't steal heat from each other in that sense. So the design would have to be significantly different, but it's possible. So any other questions there I can answer?
I see one. What are the issues preventing expansion of geothermal battery?
Expansion of geothermal battery.
I'm
not sure what the word expansion means here. Charlie's going to answer this question live. Go ahead, Charlie.
Oh, sorry, Jens, I wasn't going to be answering it. I was just marking that you had been answering it.
Oh, okay. Very good.
Yeah, I'm not sure what expansion of the geothermal battery, but if I did interpret it as expansion of geothermal into the marketplace, it's always been a geothermal battery, and we've always faced the challenge of the narrative being about loop fields being too expensive. I think we need to change the narrative to ask, why are they so undervalued? The benefits are enormous, as Jens has pointed out. And although when you go sell a geothermal system, the homeowner doesn't care about battery storage and the value of the battery, he's going to get a heck of a bargain. And we just need to change the narrative. Instead of characterizing geothermal as being expensive, we need to characterize it as being undervalued and influence the policymakers and jurisdictions that are passing codes to really characterize that value appropriately. And if it needs incentives, then great. Yeah. But I think this is so valuable that I think it should fly on its own merits. I love the incentives, I love the rebates, but fundamentally, that's not sustainable long term. We have to just appropriately value the technology.
I couldn't agree more. And you know, like I said, we always knew it, but it's the first time we quantitate it. And we also make the argument that this directly is avoiding the alternative, namely to build up an enormous amount of grid storage. But it's not just storage, it's also the electricity capacity we need to replenish the batteries and the transmission lines, etc., which needs to be added to that. So it just has a huge amount of grid value in the future. From a system grid perspective. A couple more questions here. What would be the typical depth for storing heat? We're currently going anywhere between 400 and 500 feet. That's our kind of standard loop field design depth we're using. And the data you've seen here is all coming from the loop fields at those depths between 400 and 500 feet, usually. So one says selling geothermal to industries would be a better sell to increase its adoption. Just a thought. Yes, I think utilities are starting to recognize this. I think regulators are starting to recognize it, and policymakers are starting to recognize it. And that's the really important part. Somebody took away.
Under the answer
A lot of
tab.
questions there. One says a considerable amount of energy is also lost through the sewage leaving the building. Had that been considered in our study? No, it has not, because we felt it was important on how the hot water was made to begin with, and we made it already with only a third of the energy, actually a little bit less, only about 30% of the energy. The COP of the hot water systems were around 3.25 to 3.3 on a seasonal average. It went up all the way to a 3.7 in the summertime, because the loop was considerably warmer and the heat pumps are operating much more efficiently with more energy in the loop, with more thermal energy in the loop. But we have not looked at recovering further from sewage, because we already got it down to 30%. And what else would we have? Issues preventing geothermal battery expansion, if you can make sure. Can it make sense to use heat pumps to preheat the ground loop ahead of winter storm, or pre-cool the ground loop ahead of summer heat wave? Yes, but on the other side, you saw the thermal mass in the ground is so large, it takes a while to heat it up and to cool it down. And you know, the ground loop itself was where, I mean, how would you preheat the ground loop? In order to put heat into the ground loop, you would take it from somewhere else. Where would you take it if not from out of the building in the wintertime? So I'm not sure if that concept would fly or fly well. Again, we didn't even worry about it. We just took whenever heat was available from the building, put it in there, and got it back. And this is how, really without a problem, this was operating extremely well. The ground loop was never dropping below 40 degrees. We always had a very efficient and an extreme large amount of thermal energy in the loop, no matter how long the cooling, the heat wave, not the heat wave, the cold span outside was. I mean, we're talking here, the single family homes were in Buffalo, New York, and those, even during the blizzard we had here with all those tragedies surrounded with it, we had extreme resilience. Not one of our systems went down, and we have close to 1,000 heat pump systems installed here, not a single one was actually losing its capacity or its efficiency. Keep that in mind. So it is an extremely resilient technology. And I must state that not many of the air source heat pumps were doing very well when we had 6 foot of snow here in Buffalo. That's just the nature of the beast.
Okay, you see the question from John Rath?
Okay, we're getting there.
Are all heat pumps in the building variable speed?
If not, why not?
Yeah.
And not all of them are. We are pretty much variable speed is a standard when we have a single heat pump for a single family home. And normally that's in either, 3, 4, or 5 tons. Once you get into apartment buildings, and the apartment buildings are significantly more efficient because they have a much higher density and you don't have as much outside wall per square footage. Normally, so for example, Zero Place operates with 3/4 ton heat pumps for each apartment because it's extremely well insulated. And again, it's a multifamily building. And, so the question becomes, when you only need half a ton of heating load, how much sense does a variable speed make? Maybe that changes, that we're building much smaller variable speeds in the future. The other purpose is that these are commercial heat pumps. They have not gotten that much love like the residential heat pumps have, which are selling for a much higher price. But nevertheless, I mean, we pulled this off with, single stage heat pumps here, commercial heat pumps, which are pretty much on and off. And the key recipe to the success of this and to the amazing efficiency was really the heat coming from the ground, which we view now as a thermal reservoir or a thermal battery. Can you extract heat from wastewater discharge to the sewer system? Yes, you can. Question again is, we already producing the hot water with only 30% of the energy. How much more would recovering the wastewater give to us? We certainly, if we look at Zero Place, only about 10% of the total energy is now spent on the hot water. So yes, we can get this further down by recovering the wastewater heat, but that then turns out to be maybe 5% of the entire building usage. And I think we need to look at where the energy is coming or going from, which is actually drawn the most energy, and address that problem first. Wastewater, for me, like I said, I always ask the question, how is the water heated to begin with? And if you have an extremely efficient system to do this already, maybe the value of wastewater is going down. And maybe I'm not correct with that. I'm looking forward for anybody who proves me wrong here. But like I said, we got this now down to an extreme amount, and I wanted to focus on that the loop field needs to be recognized as a thermal storage component. I'm not saying we cannot increase the efficiency even further in those buildings. Anybody else have any questions?
I do appreciate your time today, Jens, and to all the participants that joined us on our live webinar. So if we don't get another question, I'll make a motion to adjourn. And thank you, Jens. I owe you a beer.
I'm looking forward to it.